In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a large horn antenna in New Jersey. But they were plagued by a persistent, annoying hiss, a cosmic static they couldn't eliminate. They aimed their antenna at different parts of the sky. They checked their equipment. They even cleaned out the pigeon droppings inside the horn. But the faint, uniform noise remained. It seemed to be coming from everywhere at once. Unbeknownst to them, just a few miles away at Princeton University, a team of physicists was building a detector to search for the very thing they had accidentally found. It was the echo of creation itself. That persistent hiss wasn't noise. It was the oldest light in the universe, the afterglow of the Big Bang. We call it the cosmic microwave background, or CMB. Think of it as the baby picture of our universe. In its first moments, the cosmos was an incredibly hot, dense soup of particles and energy. Light was constantly bouncing off charged particles, unable to travel freely. But after 380,000 years, the universe expanded and cooled enough for atoms to form. Suddenly, the light was set free, and it has been traveling across the cosmos ever since, stretched by the expansion of space into the faint microwave glow we detect today. At first, this glow seemed perfectly uniform. But when our instruments became sensitive enough, they revealed a stunning, mottled pattern of tiny temperature differences, ripples that are only 1 part in 100,000. These ripples are the cosmic seeds from which all galaxies and galaxy clusters would eventually grow. And it's here, in these tiny ripples, that we find one of the most powerful pieces of evidence for dark matter. In the early universe, two forces were at war. Gravity was pulling matter together, trying to form clumps. At the same time, the intense radiation pressure of the hot universe was pushing it apart. For ordinary matter, the stuff that makes up stars, planets, and us, this created a sloshing effect, preventing it from clumping together too quickly. But dark matter is different. It feels the pull of gravity, but it doesn't interact with light at all. So while ordinary matter was being pushed and pulled by radiation, dark matter could quietly begin to clump together, unimpeded. It formed vast, invisible gravitational wells, a cosmic scaffolding waiting for the rest of the universe to catch up. When the universe finally cooled and the CMB was released, ordinary matter was free to fall into these pre-made gravitational blueprints laid down by the dark matter. The size, spacing, and intensity of the hot and cold spots we see in the CMB today are a perfect match for a universe where this invisible